Thank you, Giuseppe, and thanks the organizers for giving me the opportunity to come here and present my work. It's been a very exciting week, very inspiring, so thank you. So I'm going to tell you about simulating quantum dynamics, and we're going to be using generative models, in particular those frequently used in neural machine translation. Okay, and I'm going to try to motivate why, right? So these are my collaborators. So this is Di Luo from Urbana-Champaign. He was my intern during the summer. These two guys are from industry. So I'm running kind of like an experiment where I do research in quantum physics with people in companies. So they come from this startup layer 6. So it's a very interesting connection, at least for me. It's a new thing I'm trying. And this is Leandro Olita from Brazil, from Rio. So I'm going to start with this paper. So this is Feynman in 1981. So this is actually not a paper he wrote. He was giving a keynote speech at Caltech. And he asked the question, so what kind of computer we are going to use to simulate physics? And by that he meant quantum physics. Okay, and basically this is the paper where the idea of quantum computing was introduced for the first time. So it basically motivated and shaped the field of quantum computing, which is basically hoping to revolutionize computation through quantum mechanical effects. Okay, so this paper is like a milestone in quantum computing, and it's very interesting. If you haven't read it, I encourage you to read it. It's very fun. But he also asked this question that I found intriguing, is can quantum systems be probabilistically simulated by a classical computer? Okay, and that's a very fundamental question, because the answer is no. Okay, otherwise quantum computing wouldn't be what we hope it would be. Okay, and so this answer is still true today, and is fundamentally linked to the notion of quantum speed up that we're hoping to see in the next coming years. Okay, so Feynman concludes basically that you can't do this, and that the reason is because for like you to describe quantum states and quantum dynamics, you need to introduce some form of probabilistic models and some form of probability theories that can go positive and negative, which is preventing us from the ability to simulate these quantum systems. Okay, so but nevertheless, this question is very intriguing to me, and so that's what I want to try to do. Okay, so we know we can simulate quantum states and quantum dynamics exactly using probability, but can we do it approximately? So that's the question. Can we find a heuristic that we can use to, I don't know, kind of like sort of approximately realize Feynman's question? Okay, so that's the idea. And oops.
It's a button on.
I didn't use the. Okay, it's back. Okay, and so because I'm using language models, so I'm going to give you basically an example of what they do for it. Okay, so this is text generation from a neural language model. So and basically what this models do, one of the things they do is you prompt them with some text, and then they create text that is consistent with the input, sort of. Okay, so this is the prompt. So in a shocking finding, some scientists discover a herd of unicorns living in a remote, previously unexplored valley or something, right? So you write that in your input, and then this thing will produce text that is supposed to be coherent and a reasonable continuation of what you've prompted. Okay, so then this is what this model wrote. So the scientists named the population after their distinctive horn of its unicorn. Okay, and then it goes ahead, like it goes on, and it like creates this like story. It's all fake. Okay, it's dreamed by one of these models. Even very coherent. Introduced the new Professor Perez and his friends were astonished to see the unicorn. So it's very powerful, right? Like, so it's pretty coherent over like a long distance, or like over a page of text and so on. And So it means to me that these models are very powerful. Like they are producing something that is amazing and is the basis of all this hype that is surrounding neural language processing right now with all these transformers and GPT, GPT-2 and so on. So to me this is very exciting and very intriguing. So this is an example from last night, okay? So you can go to this website, it's called Talk to Transformer, and you can prompt it, okay? And so what I prompted is quantum supremacy has been, and this is supposed to complete this sentence. And basically it was motivated by a rumor there is around like the internet that Google achieved the so-called quantum supremacy, which is this, if you want, computational milestone where like a quantum computer can do something we can't with our regular computers, right? So then it completed it, right? Like, so it says like it's been seen, so it knew about the rumor in some sense. And in a series of experiments, this fake institute in Cambridge, but also at University of California in Santa Barbara, where Google has their labs, okay? So this is pretty funny, and okay, it goes ahead talking about entanglement and so on. This is all very interesting. So it generates samples from a variety of inputs close to human quality and long-range coherence of over a page or more, okay? Basically reproducing correctly the strong correlations present in language, which are traditionally, or they're known to be power law correlations, okay? So this is all correctly captured by these models, and that's, I mean, what it means is these techniques are very powerful, and they're based on neural networks, okay? So what are these models? They're basically neural networks that model language, okay? And they're basically based on these neural nets that are very powerful function approximators that can, in principle, compute any function, okay? So it is natural to ask whether we can use these models to represent complex quantum states. And we've seen already examples during the week by Frank, and we'll see more by Giuseppe and more in the afternoon. But if you want, this is also part of that stream of research. These models, what they do is they basically model this distribution of, this conditional distribution of output text conditioned on some input text, right? Like, so you prompt the system with some input text, and then it produces output text with some probability, okay? And that's how they produce this like crazy text, this fake news, if you want. You can also do translation by conditioning on, say, language Spanish, and then producing text in English, and that's basically what they do, okay? So let me tell you how I do or why I think this is kind of like natural for quantum states. So quantum states are represented by vectors in very high dimensional spaces. For a spin 1/2 system, it's a 2 to the n component vector, so it grows exponentially with the size of the system, okay? And this growth is exponential, so it's very bad, so that even solving the Schrödinger equation exactly for a quantum system with 45 spins is very challenging. So you need to use a supercomputer, and that's a big number, so big memory, exponential time, and so on. So, but language translation models live in a very high dimensional space as well, okay? And if you want the equivalence between these two exponential growths, so 2 here is the spin up or down. So here we're going to be the vocabulary size, okay? So I'm going to quote here an example from this paper called Attention is All You Need, what they claim that, or they say they're going to be using a vocabulary of 8,000 words, which is traditionally what you roughly need to understand some text, right? Like some, say, BBC articles, so not the lower level quality, but like a good, reasonably complex text, so 8,000 words, and the number of spins correspond to the length of the sentence, right? Like, so this maximum length of the sentence is going to be 100, let's say, so a paragraph, roughly, okay? And that's also a very, very large number, okay? So, so storing these distributions is, of course, impossible, so people use parameterized models, okay? So, because this requires, so I did this calculation, so this requires a computer with a memory which is exceeds in size a number of universes bigger than there are atoms in this universe. So it's very big. But this is a meaningless number, okay? And what matters is quantum states, natural language images. Natural languages are physical, right? Like we use them. They're created by us or by nature, and they have a lot of structure, meaning that most of those phrases in this high-dimensional space are meaningless, right? Like, so that they're not meaningful, and the same is true for quantum states. So most quantum states are not random vectors in this high-dimensional space. They have a lot of structure, okay? And that's what we use in quantum physics. And what we say is that the amount of information for quantum states or for language models in computer vision is just way smaller than the maximum capacity. And that's what we exploit to solve these problems. For instance, we use quantum Monte Carlo simulations where we do like a stochastic exploration of that gigantic Hilbert space. We use tensor networks where what we do is we exploit the low entanglement of states that are seen in nature, and so on. And then we know even that both quantum systems or some quantum states and some machine learning problems or neural nets in particular have a lot of even shared structure, meaning that we know that some quantum states can be represented exactly as neural nets, okay? So we know there's some common set of states that can be either found in nature but also represented as a neural net, okay? So the questions I want to ask is, can we use the power of these models for the simulation of dynamics of quantum systems? And but the other question I'm going to ask is, can we, so we've seen a lot of let's just take our generative models and make them look like a quantum state. And that's been very fruitful and so on. But I'm going to ask the question also that, the following question. So can we bring quantum theory closer to machine learning instead? So instead of changing generative models to look more like a quantum state, can we instead make quantum theory look like a generative model, okay? So that's also one question I'm going to ask. So in this talk, I'm going to introduce a formulation of quantum theory that brings quantum mechanics closer to machine learning, okay? And I'm going to use generative models, in particular RNNs and transformers, which are used in natural language processing to parameterize quantum states. And I will show an example motivated by quantum state reconstruction to exemplify what I want to do. And also I'll show you a heuristic to simulate, say, quantum computers using these models, okay? So that's what I want to tell you. So to do this, we need to introduce, tell you what a quantum state is, measurements, and how they relate to probability distributions. So usually, quantum states are represented by a density matrix that describes the statistical state of a quantum system. And everything we can possibly know about a quantum state or a quantum system is encoded in this density matrix, okay? And this is a quantum state. It's a matrix. It's a positive semi-definite Hermitian trace one acting on the state space, right? Like, so this is a density matrix, and the family of quantum states forms a convex set. For instance, for one qubit is the block sphere, okay? So the basic sphere that we study in quantum mechanics, and that's what I want. But on the other hand, can we represent the same information about the quantum state, but only with probability, okay? And the answer is it is possible, and this is through the so-called measurement positive operator value measures, POVMs, okay? And these are a family of operators M, a collection of them from A is 1 through M, and they're positive semi-definite, and they add up to the identity, okay? That's, and then the crucial connection here to experiment is the so-called Born rule. So if you measure these operators, then you can assign, on a particular quantum state row, then you can assign some probability distribution on the outcomes of the measurement, okay? So this is what, like, one example of what we see in quantum mechanics 1, that what we say is, okay, we measure the system and it comes with some probability that is proportional to a coefficient of the wave function of that particular eigenstate. So that's one instantiation of the so-called Born rule. But a more generic one, when you have mixed states and density matrices is this distribution. So if you measure M on state rho, the outcome A is going to show up with probability P, okay? So that's Bond rule. And there's also another crucial ingredient, which is informational completeness, which is what allows us to represent a quantum state in terms of probability, okay? So informationally complete P of M's means that the measurement statistics PA contains all the information about the quantum state rho, okay? So that's the most important idea here. So representing quantum state through rho or through P is fine, so long as you probe enough information about the quantum state through the measurement M, okay? So that's the idea, and the relation between rho and the distribution can be inverted if you have informationally complete measurements, okay? So all the information about a quantum state is in in P. We take measurements in particular that are tensor products of measurements when we're considering multi-qubit systems, so many spins, okay? So that's the idea. So in a graphical notation, so you have this Born rule, and what I do here is to show how to get, so here you go from rho to P, but there's a way to invert it, and this is all this diagram. So the inversion of this problem gives you this expression, and so where you write down rho in terms of the probability distributions, plus some coefficients and the measurement here. Okay, I don't want to go through the details, but what this is telling you is that you can write the quantum state in terms of a probability distribution that contains all the information about it. Okay, so that's this expression here, and this is like a graphical notation that we use, where this is the density matrix in blue, and the probability distribution is P, is this green tensor here, plus some simplified or some simple tensors that are factorized. They act on only one spin at a time, okay? And that's important for the numerical efficiency of what we're trying to do. Okay, so this is our representation of the quantum state. So we have some quantum state rho in terms of a complicated probability distribution and some simple tensors, right? So you can think about this representation as a factorization of the quantum state in terms of a probability distribution P that is complicated, and a set of tiny tensors, right? It's just the same tensor patched multiple times. As many times as qubits in your system, okay? So this is, if you want, one instance of an idea called wave function positivization that we've been using recently, where you factorize the quantum state in terms of a positive tensor and then some complex value tensors, okay? Something to highlight here is all the entanglement and potential complexity and interactability of the quantum states is in the structure of the probability distribution. So everything that produces entanglement comes from P, because the rest is all factorized. And it's kind of like efficient to handle numerically for some tasks. The other thing is the sign structure of the tiniest of the quantum state comes from the complex numbers in these tensors. Okay, so it's, so what's the insight, and why do we want to combine these two ideas with machine learning? Is because we can parameterize the statistics of the measurements in terms of a generative model, right? Like, because they're pretty powerful. So if you want, they're capable of producing very complicated distributions, right? Defined over, like, say, text or language and so on, and that's what we're going to be using. We're going to replace this probability distribution that is complicated and intractable by a neural net, by a neural network probabilistic model, by a generative model over the measurement outcomes A. Okay, so that's the insight. So we're going to replace this P by this model, and we're going to be using autoregressive models, RNNs and transformers, and because of three reasons. So one of them is because they allow for exact sampling, which is it's good to have if you want to deal with the numerics behind what we're going to show. It has a tractable density, which we need to quantify the quality of the reconstructions and so on, and because they're be very powerful, as demonstrated somehow in this field of machine learning. Okay, so we're going to be using this RNNs and so on. So we replace this part, so our quantum state, by a model parameterized by some RNN or some transformer. Okay. So this is just a brief remark. So we've been thinking about this wave function positivization, in which we do something very similar. We factorize the wave function in terms of a positive part times some tensors here that are unitary in this case. So this is just a comment about how this work relates to some of the work that we've been doing with Giacomo Torlai. So let me show you one example. So the example is learning a quantum state from measurement, which is the closest thing to machine learning we can think of. Okay, so why do we need to do this? We need to do it because we need to go beyond standard quantum state tomography reconstruction for the quantum state, because there's been recently a lot of progress in controlling quantum systems and how we measure them. Okay, and there's a lot of availability of arbitrary measurements, and they're performed with great accuracy. And the bottleneck in the process of estimation of quantum states from measurements is this curse of dimensionality, that you need an exponential amount of numbers to parameterize quantum states. And this is important for benchmarking quantum state preparations in real experiments. So here, for instance, we have an experiment with trapped ions. This is Google's latest chip. This is D-Wave, which is a quantum computing company. They all produce, say, they're trying to produce a complicated quantum state and use it for something. So you need to benchmark it. So for that, you need some sort of like benchmarking through quantum state tomography or reconstruction of the quantum state, or inference of what the quantum state looks like, and so on. So that's why we need to go beyond standard tomography if we are going to be able to benchmark these systems that are growing really fast. Okay. So, and these are examples of recent papers with 51 qubits, 53 ones, even 1,800 ones. So it's growing very fast. Okay. So what's the setting in this problem? So we prepare an unknown quantum state. So that's the experimentalist tells you, I'm going to produce this quantum state, okay? And you apply measurements that probes enough information about the quantum state. So you get some outcomes from the measurements, I don't know, like spin up, down, up and down on all the qubits. That's just one example. But this is not enough information to reconstruct the quantum state, so you have to repeat the experiment many, many times, and you measure again and again and again and again until you collect enough information such that you can, say, produce a decent estimate of the reconstruction, okay? And so what you do is you repeat these measurements, you collect a big data set with millions of measurement outcomes, and then what you do is you try to infer a quantum state. Okay, so this is where we're going to use our model. Okay, so yeah, yeah.
So when you probe the unknown quantum state, are you changing the quantum states?
Yeah, exactly. So when you measure the quantum state, you change the quantum state, you actually destroy the quantum state. So you get a measurement and the state of the quantum system changes completely, right? That's the measurement problem in quantum mechanics. And so that's why you have this step here. You repeat the experiment and collect more measurements. You do it on and on and on. So you have to assume that the state that you're producing is always the same. So you have to have enough experimental control. And then, okay, so we want to infer this quantum state. And I'm going to show you examples that are synthetically produced. So we took the ground state of the transverse field Ising model, which is a model of like in many body physics, where like you have spin 1/2 variable sigma I interacting through this Hamiltonian with next nearest neighbors and some transverse term sigma ij. So we produce the ground state numerically, and we take a collection of measurements on this simulated quantum state, and then what we're trying to do is we're trying to reconstruct what what you would observe in an experiment. Okay, so these are expectation value of correlation functions. So expectation value of sigma ix as a function of the size of the system, or the positions in the system, and so the orange is the synthetic quantum state correlation function, and these are the reconstructions from measurements on the fake or synthetically generated experimental data. Okay, and they matched relatively well, and this is using a recurrent neural network, a 3-layer gated recurrent unit RNN model. Okay, these are two-body correlation functions, and they seem to match. Okay, so here's a little bit of a more challenging experiment on a Heisenberg model in 2-dimension on the triangular lattice. So this is very interesting because the sign structure of the ground state is all complicated, right? So this is where these factorizations on the quantum state are useful, right? Because we're trying to learn a model that is only this part is all positive, and the sign structure is all encoded in these tensors. So we only need to learn a positive part of the model, because so this is challenging because when we were trying to use this complex RNNs, it was very they're very challenging to optimize. Okay, so this is kind of like an interesting feature about what we've done, in that everything that we need to optimize is all a probability distribution, so it's all positive, so there's no complex numbers. Okay, and then so nevertheless, like even if the ground state is all complicated, we're still reconstructing a quantum state with complicated signs, and these are examples of the reconstruction. So this is the synthetic state on 8x8 lattice, so it's about 64 qubits, and as you see, we're able to reconstruct this correlation functions relatively well. Okay. One example, it was interesting, but quantum theory goes beyond the representation. Okay, so we've represented quantum states, and that's all right. But quantum mechanics requires some dynamics. For instance, Schrödinger equation, it requires a description of how you measure the system. So you need measurements and so on. So we need to complete the theory somehow, right? So for that, like I started with unitary dynamics and quantum channels. So this is, if you want, the first example where I introduced dynamics. So the unitary dynamics transforms a quantum state ρ through a unitary matrix, so kind of like a rotation in quantum state space, and then you get some rotated density matrix Pu. So the question is, what happens to my representation when I apply a unitary on a quantum state, and that we can track what that does to the probability distribution, and it's basically this process, right? Like, so you go from a probability distribution representing this ρ to a time-evolved, if you want, or unitarily rotated distribution Pu. Okay, and it happens through a matrix O that depends on the unitary that you've applied. Okay, but the interesting thing is that this expression is very similar to evolution of probability distribution in classical mechanics or in classical systems. So when you do, say, for instance, Markov chain Monte Carlo, what you're doing is you're taking, you start from a very simple probability distribution, you evolve it with your transition matrix, and then you get to a complicated one. So this is very similar, but there's a difference, right? Like, so when you use Markov chain Monte Carlo, you use always your transition matrix is always a stochastic matrix, right? Like, because you interpret it as sort of like conditional probability, and but this probabilistic gates that we've derived, they're like a generalization of stochastic matrices. Mathematicians call them somewhat stochastic matrix or quasi-stochastic matrices, and they have this following property: if you trace them over the columns, they adapt to 1. Okay, as a stochastic matrix, but they can be negative, right? Like, they can be positive and negative, and this is what makes, if you want, quantum mechanics still intractable, right? Because otherwise you could simulate the effect of quantum dynamics or unitary evolution through Markov chain Monte Carlo, but we can't. Okay, so the evolution is almost classical, so somewhat classical. Okay, so so this is the fundamental equation that I want to simulate. Like, what's the evolution of probability distributions under the probabilistic, somewhat stochastic matrices? Okay, so let me go ahead. We can also derive a Schrödinger equation from the probability distribution. So if you consider a special unitary that is e to the i delta t, and you take the limit of delta t going to 0, then you derive, if you want, the equation, the Schrödinger equation for the description of the probability distribution. It is this equation here, which has a formal solution. Is just p equals e to the I a t times your initial distribution. Okay, so it's this is a solution that is basically useless because these matrices are exponentially big in general. Okay, where this is your a. And you can do open quantum dynamics. So open quantum systems, you can derive a Limblad equation for the p, and the solution is again formal, but it looks very simple. Okay. There's measurements, but let me skip the description of the measurement for now. Even if we have time, I'll discuss it at the end. So I have some time, but let me, 20 minutes, okay. So let me describe what one example of applying these generative models to the simulations of a quantum dynamical system. And I'm going to take quantum circuits and quantum computing as my first example, and my last, okay? But meaning that I could try to simulate, say, quantum dynamics or solve this Schrödinger equation with generative models and so on, but let me focus on this very simple case, which is quantum circuits, right? So as I said, what we're trying to simulate is the applications of some complicated unitary on an initial quantum state that is very simple, that produces some complicated quantum state rho u, okay? So unitary matrices are represented by u. So that, in our language, translates into time evolving the probability distribution corresponding to rho into pu, okay, through some somewhat stochastic matrix O, okay. The good news about the representation that we have is that both tensor network notation as well as quantum circuit notation translate basically 1-to-1. Okay, so if you have some tensor networks represented by this unitary tensors or any tensors in the language of probability, they translate to this probabilistic gates. Okay, so probabilistic tensors here in green, and quantum computing, which is usually written in this language of quantum circuits, translates also into a language of probabilistic circuits. Okay, and it's, so basically the language remains, which is nice. So what is a quantum circuit? So it's a notation for the evolution of an initial quantum state into a complicated one using this graphical notation. So you start from a very simple quantum state. In this case, is a tensor product of 0, 0, 0, 0, and then you start applying a sequence of simple unitary matrices acting on the initial state, and they usually are local. That's meaning that they're tensor products of the identity here and elsewhere, and these matrices act locally only on a couple of qubits, okay? And then you apply more and more and more, and then at the end you measure, and this is the outcome of your quantum computation, okay? So that's what a general computation is, and this is what a quantum algorithm looks like. It's just the choice of these unitary matrices and these gates, okay? Hopefully at the end, when you measure, you solve the problem. Okay, that's the hope with quantum computing. So now when you do translate that that process, which is written here in quantum state language, that translates into initializing a probability distribution in a product distribution, and then applying a sequence of somewhat stochastic matrices until you get some probability distribution PU, okay? And the question is, can we simulate this with, say, a transformer or a recurrent neural net? Okay, so that's what I want to do. So I want to point out here that this looks very similar to, say, Green's function Monte Carlo, but as I said, these matrices can have positive and negative entries such that you can't get this probability distribution or even sample from the distribution due to this infamous sign problem in quantum Monte Carlo. Okay. But can we do it with neural machine translation? So the idea is, okay, we take this initial distribution, we have this somewhat stochastic matrix that results in probability distribution. Okay. So what we do is, so we have the initial distribution, we introduce a model p theta, that's going to be my neural net. We compute the distance between the time-evolved model pu and this model through sampling, okay? We minimize the distance between the two, so in this case we use the Kale divergence, Kullback-Leibler divergence, and that's it, right? Like, so if we manage to make this distance very small, it means that we've found a good approximation p theta to pu, okay? That's the idea. The good news is we can compute, we cannot compute the KL, but we can compute the gradients because, so there's an entropy part that is very difficult to compute, but there's a KL that is easy, like a cross entropy term that is relatively easy that we can then try to, say, minimize using gradient descent or any of its variants, okay? From samples from the original distribution or any other distribution if you use importance sampling. And it's very basic, right? Like, it's just taking your initial distribution, you get samples or you get them from importance sampling, you compute the Kale divergence or the cross entropy and its gradients, and then you follow the gradient, okay? Yeah? So it's very easy to initialize because when we start from a product distribution, the initial state is 0, 0, 0, that translates into a product distribution, okay? And this can be easily done in say in a transformer or in an RNN, because what you can do is you can decouple the last layer, which is usually a fully connected layer with a softmax activation. And what you do is you zero out the matrix, the parameters in the matrix of the layer, and then you tune the bias to what you want according to the initial set that you have. So we can initialize the neural net exactly on this probability distribution. Okay, that's a good question. Thanks. So let me give you one example. Okay, so we're going to be preparing some simple states. They're so-called GHZ state and the linear graph state. So if you want to produce them on a quantum computer, so these are the recipes that you need to apply. So you initialize the state with the 0, 0, 0, 0, and then you apply the so-called Hadamard gate, which is this matrix here, and then control not gate, which is this one here that acts on 2 qubits. So it's a 4x4 matrix, and you do that multiple times. If you want an n-qubit GHZ state, then you apply this on and on until you this control X gates until you reach n qubits. Okay, so you can apply many times if you want. The same is true for the linear graph state. So you apply this Hadamard gates, and then some control Z gates. Okay, and these states are very interesting for 2 reasons. So one of them is they're fully entangled, so they have a lot of entanglement in them. But also they're classically tractable, so we can benchmark our preparations using probability distributions with the exact quantum states, okay? Because we can simulate them efficiently with our laptop, okay? So that's why I picked this, so that I can benchmark that what I'm doing makes sense, okay? So this is preparing the so-called Bell state. So it's only 2 qubits with 2 gates. These are simulations of this state preparation using probability, using an LSTM model with 2 stacked layers with very small number of hidden states, only 10 of them, followed by a softmax layer that represents ultimately the outcome of the measurements, okay? And this is as a function of the training. So first I start training the application of the first gate, H. So that's this first region here, and then the second region here. And as you see, the KL divergence between what I prepare with my LSTM and the exact Bell state, which is this, goes to 0 as I finalize the training, okay? Meaning that the probability distribution that I'm getting at the end corresponds to the Bell state, okay? And this is the classical fidelity, so it's a measure of distance in probability space. It's this, it's called, in statistics, it's called Bhattacharyya Coefficient. Is this object here that is 1 when the models matches this probability distribution P, and that happens again as I train the model, and around 200 epochs I get there, okay? And then there's the quantum fidelity, which is the most the strongest measurement of, say, similarity between quantum states, which is this object here. So it's trace of square root rho times sigma, which are my 2 states, and then times square root of rho again, and trace. Okay, so this one also goes to 1 as I train. And this is a proxy for the cost function that I use that doesn't seem to quite go down, but on average is very slowly going down. Okay, so that's the cost function that I use during the training of the models. So yes, that's my first example. So it's only 2 qubits, so very small. Can we go bigger, right? Because why? Because we want to be able to see how far we can push the limit of classical simulation of objects that are intrinsically quantum mechanical. Okay. So we were able. So this is again with an LSTM. So we were able to go up to 14 qubits. So that's still pretty small. But these are curves, like what people call learning curves. So as a function of how many samples you use, how many samples you get from these models for training these states, how do you get there, right? Like how fast do you learn? And so this is classical fidelity as a function of the number of samples. And as you see, as I grow the number of samples using the estimation of the gradients, this fidelity goes to 1, basically. Of course, the larger the system, the slower it goes, but eventually you get there, okay? And this is the KL divergence, again, as a function of the number of samples, so the quality of the estimation of the gradient. So what we found is that, yes, you improve as you grow, or you improve the quality of your gradients, which seems to be the most important ingredient here. You get lower and lower KL divergences, okay? So let me give you, so this is all with LSTMs and RNNs. So we also try, this is an example. So here is how many samples n star do you need to reach fidelity of 0.95 as the function of the number of qubits, okay? And this is in log, and it looks like a straight line, meaning that you need a number of samples that is not blowing exponentially but polynomially, okay? Although with a high slope. So we feed this to a straight line, it looks like a n to the 4, which is a lot, but still doesn't look horrible, albeit for a very simple quantum state, okay? So it gives a linear fit with a slope about 4, so it's high complexity but not exponentially bad. So finally, I have an example with a transformer, which is way easier to train and much more scalable. Okay, so we need to take a lot of samples from the model, and that's fine. The transformer is very slow for sampling, but for training is very fast. You can parallelize, you can use GPUs and even many GPUs for training, and so we're able to reach about 60 qubits for the preparation of the graph state. Okay, which is already beyond what you can do with the exact methods. Okay, so that's nice. You get, of course, as you go bigger, the fidelity, which is the classical fidelity, goes down, but nevertheless is not very low. Okay, this is for the G8Z state where we're able to reach up to 50 qubits. Okay, so we're pushing, and it seems that we can achieve some non-trivial results using those models. They're very powerful. Okay, so here's the bad news, the known bugs of what I've done. So the standard state space for quantum states, they live in a convex set of, as I said, trace one Hermitian positive semi-definite operators. So for 1 qubit, that corresponds to a sphere. Okay, that's the sphere here. And if you go outside the sphere in terms of like the directions in the block space, then you go to matrices that are not quantum states. Okay. Since the relation between the density matrix and the probability distribution is linear, it means that in the simplex, which is where like the probability distributions live, there is a convex set of probability distributions that correspond to quantum states, to valid quantum states. Okay, and this is the people call this Q-plex. Kind of like because they probability distributions live on a simplex. Is this plane here, but since there's a subset of probability distributions that are quantum or correspond to quantum state, they call it the Q-plex in quantum Bayesian theory. So it means that that the set should be respected during the simulations that I perform. Okay, the problem is the models that I'm using, they live on the simplex, right? Like these neural machine translations cover some distributions within the Q-plex. We know that because we've produced exact examples, but they're not restricted to live in the Q-plex, right? Like they can live anywhere, and even you can even initialize them anywhere you want almost. So that's a problem because it means that my distributions like the distribution that my algorithm produces may not correspond to valid quantum states. Okay, so the process of what I'm trying to do is, okay, this is the simplex where the neural machine translation models live. I start with an initial distribution P0 that I know is a quantum state, but then I'm trying to time evolve it along the edge of the Q-plex that corresponds to pure states, right? Like that's what quantum computing wants to do. It wants to time evolve pure states such that the final distribution is some useful quantity. But since you're doing it approximately, you may leave the Q-plex. And it's hard to determine where the model is going, right? Like that's the so-called inductive bias of the model and the approximation that you've made, right? Like, so if you get the KL divergence to be 0 at every time step, then fine, you basically simulate the problem exactly, but we can never guarantee that the KL was 0 at every time step. So you may end up with a final model P theta that is away from your desired probability distribution by some amount. Okay, so that's an issue, and this may not correspond to quantum state. So that's the first bug, or a feature, if you want. The other feature is we quantify the quality of what we do through the so-called classical fidelity, which is not as a strong metric of fidelity because it's always, inverted this thing here. It should be greater than the actual quantum fidelity. So it means that the classical fidelity that we can use is overconfident, okay? the problem is we cannot measure the exact quantum fidelity. It is intractable. So you can try to estimate it through samples from the model, but the variance of the estimator blows exponentially with the number of qubits, unfortunately. So it's not because we didn't try, but because it's very hard. Finally, maybe this is not a bug, but a feature, since this is a very inspiring paper. It's called The Learnability of Quantum States. And what they propose there is that there's some probabilistic reconstructions of the quantum state that are good enough that guarantee that this probabilistic measurements of distance are that guarantee that most of the measurements you perform on the quantum state are correct, right? Like, so, which is maybe perhaps better measurement of fidelity for the current quantum devices that are, they may have even zero quantum fidelity, but that nevertheless can be useful if you can measure, say, expectation values of local operators, as like they hope to do, say, for instance, in quantum computing for chemistry and for physics and so on, okay? So I don't have very strong opinions. I wish I could measure fidelity, but I can't. But perhaps this measurement, this classical fidelity, is not so bad for the current state of the art for quantum devices, okay? So can we simulate quantum systems with probability? The answer is still no, since evolving these distributions remains a challenge due to the sign problem from the quasi-stochastic matrices that I use. However, we've introduced a heuristic to do it, right? Like, it's just getting us closer to answering this question in the affirmative, although approximately, okay? So can we simulate systems probabilistically with a quantum classical computer? No, but our formulation of quantum theory is closer to machine learning, so we can, say, try to attempt using those powerful models to do an approximate job. Heuristic, using language translation models to simulate quantum circuits, but we can do more. The good news is the optimization problem is relatively easy, although you need a very accurate gradient as far as we've observed. Requires a lot of samples and tricks to improve the variance of the gradient, but we're working on it. So we're using control variates and important sampling, and that improves the situation. We can parallelize over multiple GPUs, which we have not done yet. So we parallelize over just one GPU. And one of the dreams is we'd like to find a generative model directly living in the Q-plex, so that it doesn't leave this blue region that I was referring to earlier. And so Outlook, so we're going to be trying to run simple quantum algorithms on the transformer, see if we can get, say, classical algorithms that are inspired by quantum computing. We're going to study real-time dynamics, Lindblad dynamics, and so on. And with that, I'd like to conclude. Thank you.